So I just want to introduce kind of the idea of what we're doing when we're doing what's called integration. So I showed you earlier that if we have a line, say it's x versus t, and we have something like, oh no, we'll do a parabola. There we go. And I showed that we can kind of think about splitting this up into different segments, which we find the rise over the run, the rise over the run. And you see that the rise over the run is actually increasing at each point. And so if we were to plot the velocity as a function of time, we'd see a line, because the slopes of these lines are increasing as time increases. And I also showed that if we want to go back this way, then you can rearrange the equation v equals x over t to x is equal to v times t. And so that means that the area under this plot here corresponds to the distance travelled. So the area corresponds to the total distance travelled. And this is a really important finding. So how can we think of doing the reverse step when we have a function which isn't a line or isn't a rectangle? What happens if I have a function that looks something like this? Another option is, in chemistry we can have functions that look like this, or that look a bit like a parabola. Say the harmonic potential. So how do we sum the area underneath this plot in order to calculate back the function? And so one way of thinking about this is you can consider rectangles. So we can think of this being split up into a whole bunch of bar graphs, and all the different bar graphs will have a different height, which is given by the height of the function, and we're going to multiply that by the width of these things, which we consider to be h. And what we're going to do is, just like before, we're going to look at the limit as h tends towards 0. And as h tends towards 0, what we do is we're actually calculating, we're summing up all of these different bars, like a bar graph, but they're getting infinitesimally small. And so that's the important thing. And so what you'll find is you'll see this symbol here. You'll see the integral sign, and you'll see the derivative in here. Let's just go with t, dt. And if we take the derivative, then that's going to be equal to our function, and that's going to be equal to a constant. Because we remember that when we went this way, when we took the derivative, if there's any constant there, that goes away when we take the derivative. And that makes sense, right? Because if we're trying to find the slope of this line here, let's just say we're trying to find the slope of the line y equals mx plus c at the point that's tangential to this point here, we take the derivative, we're only going to get m out. That's going to be the slope, and we're going to miss out how high this value is up. So we have to always make sure that we've got the c when we do an integration. The only time we can get away from that is when we're going to consider the area between 2 points, and doing that we actually subtract c from itself, and that way we can we don't have to consider c. But to begin with, we do. So we can consider, we have to look at the function's value, which is the height of this thing here, which is going to be f dash of t, and we have to multiply that by the infinitesimal unit dt. And that is going to give us the area of all of these different things. And what this symbol here means, it's the Old English S, and it means to sum. So the idea is that we want to sum up. And earlier we found that this was the symbol we had. We had the sum here, where we had, it starts from, say, 1, and it goes to some value n. And in this case, we'd have f dash of t. Let's just say t starts at 1. Sorry, and we times that by a small amount dt. And so we're going to sum up along the value all of these infinitesimally small sections to give us the area under this plot. And the best thing about this is that it is literally just the inverse of differentiation. So you learnt rules about how if you differentiate, say, the sine function, it goes to the cos function, and that's differentiation. But if you want to integrate, it's the opposite. So cos will actually go to sine, and so this is how we do integration. And we can calculate this using the same form we had before, but you don't need to know that. I think the most important thing is that you know just the basic concept, that we're trying to find out the area underneath these plots, and that is going to give us the idea of what integration is. And so I'm going to give a few examples next about how this relates to thermodynamics, where we want to find the area under a plot, and that way we can work our way back to what the initial function is.